reasonable models to exist is, on the one hand, access to compute power. So we have lots and lots of GPUs nowadays. That was the initial plenary discussion around the data centers. And the second thing that we have is that we have much more data that's available to train all of these models. This was a seminal paper by Jared Kaplan 5 years ago, in which this term called scaling laws was initially coined and then also popularized. The idea being that as we increase the amount of compute that's available to train our neural networks, or the amount of data size, or the size of the neural network, the performance actually increases quite quickly. And that's something that you can see on all of these plots, that basically the loss on the testing set goes down rapidly as you increase the data set size or any of the other things. One thing that you can notice is that if you look at the data set size, then this is already going from the hundreds of millions of tokens to billions and even more tokens nowadays in the training of these very large neural networks. And that's something that we are very far away from in the energy sector. Other domains have really invested a lot of money and a lot of time in the creation of these open data sets that can then be used as benchmarks, but also to create these models from scratch. So this is an example from the vision community, where a lot of effort was spent in the creation of these open source benchmarks as well as data sets. So this one is specifically called the ImageNet dataset. Same for the language community as well, where we see all these large data sets that have been created, which basically span the entire internet at this point, on which ChatGPT and other types of large language models have been created. But that's not really where the curation of data stops, because these models also learn directly from their interactions with humans, as well as with the real world. So that's really something that we are missing in the energy sector at the moment. We have seen the importance of increasing training data in the energy sector as well. So this is a very brief example from our own work on creating solar forecast algorithms. And then you can see on the x-axis we have the amount of data, and on the y-axis you have the loss. And if you try to train a simple neural network, then basically you see that it takes quite a lot of training data before this model can converge to a good solution. And before it has happened, you really cannot use this model for operational reasons. We have seen the same results for other types of things as well, like grid models basically, but also controllers interacting with those grid models, and also models for distributed energy resources like heat pumps. But I will leave that to later when Chris is going to talk about this in more detail. So that brings me to the agenda for the session. We have around 1 hour and 10-15 minutes still left. We started a bit late, so maybe we will be running a bit late as well, but we'll try to keep to time as much as possible. So we have 5 talks. The first one is going to be by Chris de Velder, who is a professor at Ghent University, where he works on data efficient and interpretable control for distributed energy resources. The second talk is going to be, the second talk is going to be by Hisham Jura, who is an associate professor at Aalborg University and is also a researcher at SINTEF Norway. And he's going to talk about some Scandinavian learnings about open data in the building community as well. Then we will shift gears and we will start talking about the grid perspective, so what is happening from the grid side, where Professor Martha Vannin from KU Leuven is going to talk about learning grid representations from limited amounts of data. And we'll also hear from Leander from JACO, who is going to give us a brief perspective on how Dutch distribution system operator, which is at the forefront of these problems with AI and control and grid congestions, is trying to approach this problem. Finally, we'll conclude with Dr. Umar Hashmi, who is going to talk about a future in which we may have access to a lot of data, and how will we get there, but also what do we do once we get there. After that, we'll round up the session with a panel discussion. Right, thank you. And Chris, the floor is yours. Thanks for saying.
Okay, thanks. Does this mic work? Yeah, now it does. Okay, welcome also from my side. So I'm indeed Chris de Velder from Ghent University, also affiliated with IMEC in Belgium. And I'll be talking to you about what we've been doing in the space that Hussein already indicated, which is controlling flexible assets. Could be heat pumps, could be EV chargers, could be batteries, and so on and so forth. I'll briefly skim over the context, because at this conference you're all quite familiar with it. So the challenges the grid is facing or has been facing for even over a decade is the introduction of renewable sources, and next to that also on the side of the demand side, a lot of things have been happening, a lot of electrification has been going on. I already mentioned the heat pumps, mobility is another sector that you can see on the slide is quite substantial or getting more and more substantial also in Belgium. So that's creating these challenges. One of the solutions are to deal with this, or what this creates is an environment where you need to also control the demand rather than purely the supply. So you can decouple those by having storage, may or may not be cost effective. So what we are looking at from our side is mostly demand side management kind of techniques. So basically controlling these flexible assets. So I will be talking to you about three things. The first thing will be dealing with how to learn an effective policy to control, for instance, a heat pump, as Hussein already alluded to, in environments where still today we don't have that much data yet. So the question there is, how can you efficiently train, and where efficiently means using not too much data or learning maximally from a limited amount of data, how can you do that? And then next on I will be also talking about two other topics, but we'll come to that later. So first part is how to learn from limited data, in this use case specifically for heat pump control. So one scenario, just to sketch the context, in a residential setting, you want to control your heat pump to obviously respect the user comfort levels, but effectively also to try and minimize cost, for instance, under time varying prices, which is a plausible scenario today. The techniques we've been using at our lab mostly involve reinforcement learning, so that's a data-driven technique, which means you need data to learn from. This part of the presentation will go about how to use efficiently the little amount of data that you may have. Quick primer on RL, reinforcement learning, for those not familiar with it. The basic principle is that you let an agent, so this technique was originally a lot used and developed in kind of gaming environments, hence this representation. Obviously, we'll be talking about home energy management here. So our agent is our home energy management agent that needs to control a couple of assets, in this case, particularly the heat pump, for instance, or the battery in later cases, but here heat pump, to minimize this cost under time varying prices. How an RL agent learns to do this is it learns from experience, so it interacts with the system, it applies an action, which is replicated there by this blue arrow. Then, based on the current state, that might be the current temperature, a history of previous actions, and so on and so forth, environmental variables like outside temperature, potentially forecast thereof, and so on and so forth. So that's your state. Agent, based on that state, takes an action, gets a reward, or in this case, gets the cost, which we're trying to minimize. And then from trying different actions, gradually this agent learns. And obviously it needs data, so you can do this offline, collect data, historical data, and then train your algorithm this way. So that's what this is about. And what we've been looking into in one of the papers was cited on the title slide a few slides back, which these slides, by the way, are already on my website, so if you want to look into the references, you can look them up there. So what we did here is, well, the basic idea is we encode the state, which might encompass a lot of variables, into what is called an embedding. So we're using an encoder, represented by the yellow block there. And we first train that encoder not on the control task, but just learning the behavior of the system, in this case, the house and the indoor temperature. So try to predict finally the temperature based on the current state, which we first convert and code into this embedding. And one of the variables that we explicitly make part of that embedding, of that compact representation, is the building mass temperature, which in practice you can't measure, but we know some physics equations where we can tie this mass temperature into, And it's like a first order system, like a 1R, 1C model, I think, if I'm seeing this correctly on the slide. So we have basically a physical model, a simplified model, but what we try to do is let the representation of specifically this building mass temperature respect these equations. So we learn the parameters such that whatever we predict as building mass temperature and our final temperature predictions, that these all together fit the physics equations. And then in a second step, so that's the idea that I just mentioned, so then we learn to efficiently represent the state of the system, basically, which we can use to make predictions. But what we want to do is not make those predictions, but determine a good action, which is then represented by this Q function, which we also learn and model in a neural network, so this green block. But the key is that we use that same embedding there. And that, as I will show on the next slide, allows us to learn faster than purely from data without infusing this physics knowledge. So that's this physics-informed model that we created. We benchmark it against black box models. So here you see a snapshot of, I think, a few days. What happens, on the bottom slide, you see the action. So the blue, either we turn the heat pump off or on. The black curve on the bottom there is a price. So ideally, you only turn it on or mostly turn it on when prices are relatively low, and you see that that's what's happening. On the top, then you see the temperature evolution, which nicely stays within these user comfort bands. So qualitatively, it seems to be doing what it needs to. Summarizing our results on the right-hand side, what is plotted there, it's the normalized cost, so lower is better on the y-axis, for an increasing amount of training data. The black lines are for the black box model, the orange line is for physics informed, and then we see, especially in low data regimes, we attain lower training data regimes, we attain lower costs, so we effectively learn faster from this limited amount of training data. That's the principle I wanted to highlight here. So that's one challenge. One other challenge we're working on related to data-driven learning is, in the end, even with this physics-informed model, the components are still neural networks, which are black box, so it's hard to explain to a user, this is why exactly this action, in this case turning on the heat pump, was taken, or this is why we charge your battery at this point in time if you have a battery system. So we've also been looking into how to come up with more explainable, more interpretable techniques, and this is what we're doing here. So the case here is, I think the example will be solely on, or mostly focusing on the battery. You can apply the same system or same techniques to different environments, combining heat pumps and batteries and so on and so forth. But we're still using RL initially, but the idea is, rather than having a black box, which is modeled there as this graph of the neurons in the neural network, of mapping the state to an action, what we want to do is replace this with something that is easier to interpret. And one thing that is more easy to interpret is a decision tree, which just says, if this, then do that, else do something else. So if you plot this decision tree, it's already more clear to see, or eventually also a better starting point to try and explain why a certain action, which would be the leaves of this tree, was taken. So this is an example for battery control, a very hypothetical scenario with just a limited depth tree. And you see the kind of variables that we're checking. For instance, what is, so in this case, as I highlighted on the figure, we have a solar panel. The idea is, in this case, to maximally use the available locally generated power, which will drive down the cost. What you see here, the first node checks the normalized power of that PV panel. So if it's above this close to 50%, so meaning a solar production is quite high. If our load is rather low, then we end up in this green highlighted node, and the action being taken is charging at a 50% power. So you can translate this basically, if it's sunny and your load is low, then charge a battery. So this becomes already more easy to interpret such a tree rather than a black box. So what we're doing is we train initially this black box model, and then in second step, we translate or convert that learned policy, this black box, to, or we try to do that, to translate it to a decision tree, which would look like something on the previous slide. How to do it, I will not talk about that. You can check the references or papers to figure that out, but that's the general principle, and here are some results. So what you're seeing here is a DQN. It's a particular RL technique, so that's a black box neural network technique. And then the DDT is distilled decision trees from that learned policy with varying depth. So deeper trees allow more fine granular actions, of course. What you see here is that by converting your black box to such one of those trees, you slightly end up with a slightly higher cost, still lower than a simple rule-based controller, luckily. This increase in cost is obviously expected because your policy will be a bit more coarse because it's based on this limited depth tree. But if you look at the policies, which are visualized on the right-hand side, so this is partitioning the state in terms of state of charge on the x-axis, the cost, so the current time slot price, and then for 3 load scenarios. The bottom shows what the policy, the black box policy, is doing. The top ones are for the decision trees, so there's much clearer and more coarse and strict linear boundaries, of course, because it's just checking one variable at a time. So these are simpler policies which are simpler to explain to an end user, for instance, and do not come with a huge cost penalty. That was part 2 of my presentation, and I want to conclude with saying that, whatever I've presented before, the studies we do are mostly based on simulations, but we also try to validate these techniques in real environments, and one of those that we typically use to do small-scale experiments is a facility we have at our own university campus in Ghent. So it's actually just a house, basically, which has been instrumented with a lot of sensors, and also used for other purposes than just energy-related studies. But for our studies, what matters is, we have solar installation, we have heat pump there, we have a battery that we can control, there will be an EV charger as well, and so on and so forth soon. Here you see pictures of the actual equipment. So what we've done, or what one of my students, Toon, who's pictured on one of the previous slides, has done, is made it easy to deploy the same code, the same algorithms that we use for simulations, to run the policies on the actual house. So what he's done is built some interfacing to easily plug in whatever standards or customized RL technique that we've been working on to deploy that easily in a real environment by adhering basically to a standardized interface, which people familiar with the RL work might know. So it's basically the same interface that OpenAI gyms are using. So we can, anything that can work with those environments can also directly work with our house. And obviously we can easily also swap in the actual environment with simulated environments with some more detailed model of the heat pump, for instance, which is pictured on the bottom of the slide. And one case, but for that I'll refer to a paper of my students, using this battery controller, we validated the controller in the real environment, and some things we can then notice, as listed on the bottom, is that there are some communication latencies which affect your performance and make it go a bit below the theoretical one that we derive from simulations, and so on and so forth. And with that, I want to conclude, so thanks, and I'll leave the floor to the next speaker.
Yes, perfect. So my name is Isham from Sintef in Norway, and I'm from the building side, so I'm going to talk a bit more about initiatives to gather data from the buildings and to share it in Norway, and well, that is also applicable elsewhere. So I'm from the building side. The building is one of the largest energy user in the society and connected to the grid, also generates a lot of CO2. And it has a massive impact and also potential to help the grids, different energy grids, electricity and district heating and cooling, to perform better. So, of course, the buildings, the end users in the buildings are this key target to help the grid to operate better and to realize the energy transition. So we have this emergence of smart buildings and smart cities. They produce a lot of data and they have a lot of promises. AI and machine learning application, occupant-centric control, building to grid services, demand forecasting, demand responses, and so on. But to develop and to deploy and to make all of those solutions to work, we need some data to train and benchmark all the solutions. Unfortunately, when you start diving into specific needs or specific application, you start looking for data and then you don't find it or not in sufficient quantity and quality. So for example, fault detection and diagnosis in buildings, you have some data sets, but it's like on very specific systems, it's in very specific countries, and it's not necessarily available in the open. And for demand response, it's the same. So, for example, for the Annex 81, we looked at hundreds of potential sources, and then you start asking, like, where is this data set? Is it available? Does it have proper documentation? And then we realize it's not there. It's not what you think. It's not accessible because you were not part of the project, and so on and so on. So at the end, you have almost nothing or not enough to train and to test and benchmark your solutions. When you come to clients, people in the buildings, they say, yeah, we have tons of data. Yes, they have a lot of data files, but they promise that it's well organized with nice metadata and clearly labeled, and in practice, it's just a mess, a bunch of different files. Things are not translated, not labeled properly, the units are missing, it's just a mess. And unfortunately, it's very common in the building sector. So there is a need to collect, to structure, to curate, and to share good quality data, and that takes a lot of time and effort, but well, we have to do it. So in Norway, like in many other countries, this data might be siloed and spread in different places, and there is a need to bring it all together in a structured way. And that's what has been done, or what is being done in this initiative, this project. It's called Smart Building Hub. So it's an e-infrastructure that aims to collect, to process, to curate data from as many buildings as possible in Norway, and to make it available to the public for research and also development of innovation and technology. So it's a fairly large project, 27 million Norwegian kroner, so 2.5 million euros, with a lot of partners, research partners, and a lot of data providers, the DSO, TSO, municipalities, authorities, and also different projects. So we try to all come all together and try to collect and put together as much data as possible. So of course we have very large ambitions. We want to bring all types of data from the utility companies, electricity, district heating, district cooling, the metadata, the weather data, the indoor environment, what's going on in the buildings, at the price forecast and everything across the millions and millions of different buildings in Norway. Well, that's the dream. Of course, in reality, at least at the moment, it's a bit more modest. So we are aggregating hundreds of thousands of buildings' energy meters, aggregated at a certain level, like district level, for example. Then we also have thousands of buildings where we have the electricity and district heating data per building. And then we have fewer building and pilots where we have the information at the system level, and also some other buildings, like for example, living labs, where we know everything at the plug level, and also indoor environment and so on. So we collect that data, we curate it, we test, verify that it is of good quality, we put it all together, and at the moment we have electricity data, district heating, and the registry information, so the data, the main characteristics of the building, where they're located, and so on. And we create semantic data models so that it's structured in a proper way, so that it can be useful. And we have a bit of more information on some of the key pilot buildings. What can you do with that data? Rich data from buildings. So of course you can map the energy performance and indoor environment performance of the buildings across the country or across cities, for example. It can be used for energy planning systems, also to train certain models to predict the forecasting energy demand at the building level or per archetypes, and also to assess the energy flexibility potential of different types of buildings or clusters of buildings. Can also be used to train different black box models, pre-training and then using transfer learning. And you can also be used to train or validate or help with model predictive control. Future development, of course, we want to integrate more and more of the data, especially including temperature and air quality in the data set, and also move towards including sustainability data, CO2 impact, and we can also leverage all that data, provide different services. How do you disaggregate the use of the energy? So do you have district heating used for domestic hot water, for space heating? Where is the EV charging and so on? So we want to include more and more all of that, and can be also used to estimate sufficiency. Where is it that you have vacant neighborhoods with low occupancy? How can you renovate better? Where are the key target for renovation and improving the built environment? We have some enablers, stuff that we're pushing forward, that were positive, that helped to create all that. One thing is that in Scandinavia, there is trust. That's very important, trust. People usually trust each other, they trust the system, they trust the authorities, so it's much easier to convince them to provide us with the data. And for example, SINTEF, which is a research institute, it's perceived, just like universities, it's perceived as a trustworthy entity, and therefore people are willing to give you the data so that you can use it for the greater good. There is also good political will to push to have this data available so that you can use it to run all sorts of research and optimization. And so it's possible to have quite a nice analysis without anonymization, and then you have to anonymize the results, of course. And there is a strong demand for that data, especially that is well structured, so that you can readily use it without spending too much time on doing data curation and data cleaning and data engineering. Of course, there are also barriers and challenges. The first one is that, well, not everything is automated, so you still need quite a lot of manual time, human time to create the pipelines for the different providers. Every time you have a new provider, a new data source, you have to create a new pipeline, you have to create the data, verify it, and so on and so on. But you need even more time to talk to the people, to reassure them that it's going to be fine, there's no data leakage, to reinforce that trust. It still takes a lot of people-to-people communication skills and time to enable that. Also, sometimes there is still some worries about anonymization and the level of disaggregation or aggregation for sharing the data, and it is not clear what are those levels at the national level. So people, sometimes they say you can't go below 5 buildings, sometimes they say not below 500 buildings. It's still a bit not clear. Data quality, at least the claim of the different data provider, this is also an issue. Usually, this is a rule of thumb, but a ratio 10:1. So they say we have 10,000 cases that is super high quality, and in practice it's only 1,000 cases. So this is quite common to have that. You're usually a bit disappointed of the amount. But still better than nothing. UX design as well, in a way that the end users has to be able to download the data and use the data in an environment or with tools that he or she is used to. And the business models. So of course, we want to have the data as open and as free as possible, but the infrastructure of gathering the data and storing the data for millions of buildings that costs something. So it's like finding this balance between like certain services or certain level of disaggregation or certain clients. They should pay a little bit to support the infrastructure so that it is available for the greater amount of people. How do we create that? How is it? How do we make pricing that is clear and fair to everyone? That's also a challenge. It's work in progress. Quickly, some other open science and open data initiative that we have at SINTEF. We really try to, as much as possible, to curate those data sets and make it available to everyone. So we have a project upcoming, Janitor, about creating data set on fault detection and diagnosis in systems and buildings, which is currently really lacking, especially for Scandinavia and Norway. The different annex, IEA, EBC annex, also working on curating data sets. So for example, Annex 82 and 96 on having energy flexibility of many cases with the counterfactual scenario where there is no flexibility. It will be published very soon. We publish regularly curated data set of buildings and clusters of buildings with as high granularity as possible behind the meter. We publish tens of thousands of charging stations. There's a lot of EVs in Norway, so we try to gather that data and also curate it and make it available. And more buildings, a data set with energy demand and weather and indoor environment. We have PV as well in Norway, and since it's like on quite different latitude, having information at different latitude is very important. So we're also trying to curate and publish that of actual data from real building in real condition. And also we have some computer vision a data set for very specific use. So for example, if you want to detect the thermal comfort of people, how they are, what clothing, what activity they are doing, that influences a lot how you control smartly a building. And there is no data set for that, so we generate those data sets, curate them, and then publish them so it can be used for fine-tuning pre-trained DNNs, for example. Thank you very much for your attention. You can access the Smart Building Hub a website with this QR code, and of course contact me if you have any other questions. Thank you.
Yeah. So thank you. We move from buildings to grids. I'm Marta van In, assistant professor at KU Leuven in Belgium as well. This presentation is mostly about data quality and availability issues for distribution network research and practice. And data quality issues are both present really at the network data level, so the physical properties of the grids and their layout, as well as the measurements. We're going to have a look at both. So if you're not familiar, here are 3 types of common data quality issues that distribution network operators have in their currently available data set. So oftentimes in low voltage networks, there are low voltage users that are attributed to the wrong feeder or piece of feeder than they're actually connected to, and this is what you see on the left. In the middle figure is a depiction of the issue of not having available phase labels, so single phase users may be connected to phase A, B, C. Usually we do not know for sure. And the very last one is about the unavailability usually of inaccurate impedance data, and this is because the grids are relatively old, so oftentimes we do not know what cable has been placed a few decades ago at a certain location in the network. So all these are pretty intuitive, common issues. However, they have quite some major implications. There are more. This is a more comprehensive list. But let's say this was to give a bit of an idea of what we're talking about. If you work in transmission, this is of course not the case for transmission networks, and in distribution systems this wasn't really a problem prior to the energy transition, because these networks were managed with fits and forget approaches. But now that we need more visibility and advanced computational tools for distribution networks, these are becoming an issue. And the implications extend from researchers or actually software method developers that then deploy their methods in the field and get unexpected results with respect to their simulations. It raises some questions about the quality of open data that utilities make available, such as whether their impedances are really representative. And most importantly, of course, the major challenges are for the network operators who will get untrustworthy results from any calculation they use this data for if they contain errors. So in the last few years, there's been increasing interest in system identification, parameter estimation. They're often used as synonyms. Here specifically, I will look into parameter estimation, but you could estimate topologies, phase labels, whatever. So if you're a researcher working on this, your setup for a novel method in your paper would probably look like something like this. You take network data from somewhere and active and reactive power profiles. With these, you run a power flow, you extract the voltage magnitude information from the power flow, and you stack vector of measurements that include both your power and voltage data. For other applications, you don't need voltage data. For system identification, you do. Hopefully, you add some noise to this measurement, and then you run your estimation method, whatever it is that you're estimating, and you come up with a calculated model, which hopefully is somewhere close to the network data that you used to run the power flow in the first place. And then you validate, you check that the impedances are similar, you check the power flow results run with the two models are similar, and you, well, might be happy that, or not, about the performance of your method. So these days, realistically, you're probably using open data for the networks and the P&Q profiles, but chances are high you haven't made your actual noisy input data available to the research community. And this is quite problematic because, particularly for voltage measurements, there's quite a few issues that really might compromise even a well-performing, well-designed estimation method. And this is, however, the reality of measurements in distribution networks, and I'm going to discuss some of the issues over here. So on this toy low voltage network, you see we have 100% smart meter coverage, as you might have pretty soon in your home country. However, even if you measure all the users, you're still not measuring all the nodes in your system, so you have little to no redundancy, which means, for instance, that if one of your measurement point is corrupted, you do not have enough other information to adjust it, so this will have a pretty bad impact even on your well-designed estimation method. Then smart meters or similar devices only give average measurements with pretty limited information, really. And in the particular case of voltage measurements, the signal-to-noise ratio is quite problematic. So to give an example of the latter again, an error of 0.5%, which is more or less where the current smart meters right now live, corresponds to more than 1 volt in a 230 volt network, which often enough is comparable to the voltage drops across adjacent buses in the network. So if you try to learn on a modestly loaded network something that has such an error, you can imagine that, of course, oftentimes you cannot distinguish between the noise and the actual information stemming from the impedance. So it is quite crucial that if you develop something like this, you disclose the voltage measurement time series with and without noise. So give, well, ideally the whole CSV file of the time series, or at least some illustration like the one on the right. And even better, together with that, disclose the code as well. This is not very often the case. Originally, I also intended to talk a bit about how to compensate for this non-idealities of digital telemetry in distribution networks. Interestingly, they go very much in the direction of what the building speakers before me have talked about. In the specific case of impedance estimation, some personal experiment that I did showed that if you have a fair guess about the construction type of the cables in your system, their material, and whether they are overhead lines or underground cables, you can already get a much more reliable and faster estimate of the impedance matrices that you need for your power flow calculations and similar. However, well, still a lot to do in this space, and there is still, well, a bit of a question about what is synthetic and non-synthetic data. So there exist, of course, non-synthetic data sets, but what they usually mean is that the network data comes from a utility, the P&Q data have been measured, so they are non-synthetic. But again, for system identification purposes, we still need voltage measurements, and these remain synthetic in such a setting, which means that then, well, researchers can play a little bit with the voltage drops and the noise, and of course, if they do not make these open, it's hard to reproduce, it's hard to justify very accurate impedance or other parameter estimates, considering the non-idealities of realistic digital telemetry. However, who has this data is, of course, the utilities sometimes. So it would help to have full non-synthetic data sets for this application. So really the whole set, power measurements, voltage measurements, and the network that they refer to. And having such data opened to another very interesting challenge, which is how do we validate those estimates on these real, fully non-synthetic data. Of course, if you have a ground truth model that you have used to generate your power flow from which you extract the voltages, you can always double check your estimates with respect to your ground truth network. In real life, you can't do it. You never know the ground truth, otherwise you wouldn't be doing parameter estimation in the first place. So how do we validate that? And because of the lack of the existing data sets with the full set of non-synthetic data, this is very much an open question. I would like to conclude with some personal numerical experiments that I did the one time, or well, one of the very few times where I did get this full non-synthetic data set, and that is using state estimation. So state estimation residuals give an indication of how the estimates of a certain electric variable and the relative measurements are, well, consistent. And here you see that using the original utility network models, these residuals, so the objective value here is the sum of the residuals, is quite high. After we estimate the phase connectivity, it went down considerably, and even further after adding the impedance estimation. So this is one example, one of the very few examples. And again, this is just because there is really still a lot of room for other methods and improvements, but without these data sets and the collaboration with utilities, it is not really possible. So on that bombshell, to the utility.
Hello everyone. While waiting for the slides, I can already introduce myself. My name is Jacco Heres. I am a data scientist working at Alliander, utility DSO in the Netherlands. And I'm both working in a team where we try to get the insight of the loads of our whole grid from low to high as good as possible. Using all the measurements, smart meter data, everything that we can get. And I'm also one of the leads of our AI for Energy Grids lab, where we collaborate with several universities to do applied research for AI and get to, in order to make the energy transition happen. And so I want to talk about a bit about open data and open source tooling, how we do it. But I wanted to start with why we are want to collaborate with other parties in the world. And to give a bit of context, this is our problem. Our highest priority at the moment is that in large parts of the Netherlands there's a waiting list for large customers. You see two maps. On the left is the map for consumption of electricity, new customers that are wanting to get a grid connection. In all the red areas, there's no room left at the moment for large customers. In the orange, there might be, but we're still looking into it. And the yellow ones, we are close to the limits. And these are only the limits for the DSO grids. There are also limits for the TSO level grids, and there so. In practice, there are very few locations in the Netherlands where you can, as a large company, can get a new or large an extra large grid connection. Now, usually you have to wait for a few up to 5 years. And so we can really use help to solve these issues, to get more people onto the grid faster, to extend our grids faster. To see what room is available in the grid. And open source tooling and open data can help with this, because we cannot do this alone, the problems are too big. But we found out that commercial collaborations are sometimes a bit difficult because we're regulated, so we cannot earn things from our own models, making it commercially available. And also on the way around, it has some difficulties. We do collaborate with academia a lot, but we see also that because there's no data available, sometimes the research is not very applicable, because it assumes complete data availability or 100% perfect data, which is not in reality. And as discussed before, we need for AI models need more data, and even then we have a lot of data. We have, for instance, smart meter data of 1.5 million customers, but that's not enough to train really complicated AI models. We need to collaborate to get more data to get better models. But yeah, we don't publish all our data, and not all our tools are open. Probably you can guess that privacy and security, especially smart meter data, is privacy sensitive. We don't open our doors of the secondary substations for everyone. Electricity grid can be dangerous, and we want to also keep it secure. But it's also a part. That quite a lot of code could be made available, or data could be made available. But it's also sort of cold water, fear of cold feet, that people think like, if I'm not sure whether I can publish this or make it available, it's a bit of extra work. Let's not do it. Because there might be some risk that I don't know of, and what do I gain from it, and I don't know how this works. So a few years ago, we as Alliander, we got an open source project office, which did those support other teams who would like to make their code open source. And how do they do this? And they also help promoting the tools that are already available, so that they're also used outside Alliander by other companies or by researchers. And we joined the Linux Energy Foundation, which is a collaboration of universities and companies who work on open source tooling. And for instance, we have two tools made available, one on short-term energy forecasting called OpenStaff. And later on, we also made a tool on very fast load flow and state estimation calculations. It's called the power grid model. That's now also used in other companies, and then really this proved for us that with commercial tooling we never could have done this, but now we build things that are also used by others, and it's get improved by others. Other people say, I found a small bug in your code. Could you please improve it? That already helps us in improving our own models for ourselves as well. And yeah, we didn't publish everything all at once. We just started small, and that really helped. Like, when you have one good example, there are more that are following. So we're now also looking into where you can publish a small algorithm where you can disaggregate smart meter data into consumption and solar generation. Because we see that there are good examples before us, then we can follow that up. And on on data, we also publish some data sets, not very big ones yet, but could be useful. We're still looking in what are right platforms to publish this data, and in what format is it could we best publish it. We also do a lot of some research on synthetic data, using AI models to generate data. We also, especially for smart meter data, that could be interesting. We also here joined an existing LF Energy project called OpenSynth that's aimed at synthetic open smart meter data and other grid data. And yeah, it is quite an active field in which we are working into, because from next year on, at least in the Netherlands, it will be an obligatory, or one of our legal tasks to share data to the public, to people requesting data to us. So really, there are several teams within our company just busy in what data can we share, how do we share it, to whom can we share it, in what format. It's really one active area where we're working at the moment. And for instance, we're also now looking into a new call within the Netherlands that's also called data sharing for the energy transition, which we try to overcome certain barriers that we see. For instance, we now have sometimes a problem that different regulations is obstructing each other. We might overcome the privacy regulation, but then the non-commercial obstruction, we might have other legislation that prevents us from publishing data. I want to say a little bit more about synthetic smart meter data, because here it really links the two topics of open code and open data. Why don't we publish smart meter data? Because even anonymous data can be privacy sensitive. You can recognize certain patterns that are very specific for a certain customer. And also for ourselves, it helps that we don't have measurements for all customers, so it helps us estimating the load of customers there where we don't have any measurements from better. We collaborate in the OpenSynth project on this, and the goals of OpenSynth are threefold. Just share these synthetic data sets, but also share the algorithms to generate synthetic data. And the third is maybe the most important: develop good tests to see what synthetic data is really good synthetic data. What level do we need? And we usually split this into three fields: the fidelity checks, where we check is the data looks like real data. Utility, can we use it to real data? Can we train an AI model on synthetic data, and will it be equally good, for instance, if it would be retrained on real data? And lastly, the privacy checks, which is also not easy. Can we really prove that a synthetic profile is different enough from real profiles, or did it just overfit and replicate the training data? And recently, OpenSynth expanded its field to also grid data. So the RTE TSO published a data set that has a topology in it, a real topology, but coupled to synthetic time series. So also, expanding the field, not only smart meter data is in there, but also other grid data. And we are together with TU Delft now very close in publishing a data set from synthetic data sets of loads and generation from large customers. And that's trained on our data. And I think one of the first data sets of non-households consumers that could be made available very soon. I also had some questions for you. What could we use from you that are not working maybe at the DSO? It would really help for us if we get a clear view on what is the highest priority of data that could be shared. We cannot work on everything, but if we have a focus that we could work on, that would really help. It really helps if you join the project that are already are open source and give feedback and create issues if something's not working. Give ideas how tools could be extended. That also gives us the feeling, this is really used, and then we can put more effort into existing tools, but also new ones. And so we're looking for use cases for this new projects for sharing data, overcoming barriers to publish data, to share data with other parties. That was my last slide. Thank you for your attention. I've put here some email addresses if you want to come in contact and with the AI lab or the open source project office of Alliander. Thank you for your time.
Thank you. My name is Umar Hashmi. I'm a senior researcher at KU Leuven and Energiville. And I'll be talking about the data needs for making better decisions in distribution network. And as the curse of the last speaker in the panel, I might rush through some of the slides. So apologies for that. I'll be talking about what data types in distribution network, framework of decision making, and then sources of uncertainty that we have, and why do we need representative feeders or load profiles, and finishing my presentation with concluding remarks. So we can categorize, of course, this categorization is not universal. We can categorize the data types in distribution network into, say, static or historical data, which can be the network topology, the historical load information, asset information, topology of the network, and so on. And most of the time, we use these asset information or the static data to make decisions in distribution network. The second category could be the dynamic or operational data, which typically leads is the SCADA or AMI measurements in real time, which system operators use from their control rooms. And often these information is not available for any sort of application. And the lastly is the external and emerging data sources, which could be the weather data, solar insolation, or the location of the assets, and so on. And these are controlled by some third-party information managers. So my presentation, I'll be focusing on the first primarily, and also linking into the third. And we will not be touching into the dynamic or operational data, as it does not is often available for usage. So when we say a distribution network decision support, what does it mean? So it means that we select different types of network, and these networks could have different levels of observability. For example, what does observability means? Do we have measurements in these networks or not? And once we have certain measurements, or is it partially observable, we try to apply parameter estimation algorithms to fix the network layout. Once we have the network layout, what we want is what load profiles do we need to select. So this can lead to a forecasting block or a historical load profile block, which merges this with, say, some power flow or physics-based power exchange in the network. And with this, combining these three blocks, we try to make certain operational decisions or planning decisions. Now, these operational decisions could be how much flexibility do we need, how much congestion are we going to face in the distribution network, and so on. Our planning application is, do we need to place a storage at certain location? Is it beneficial for the system operator to do so or not? Now, these decisions that we have to make in distribution network can be considering different levels of uncertainty. These can be deterministic or stochastic, or there are many variants. Now, this problem as such is a merge or intermixing of many fields. It can be data analytics, uncertainty quantification, and power system optimization, and so on. So we need to think that this is a big problem in itself. Now, just to reiterate from my previous slides, there are various aspects of uncertainties that we need to consider. One example could be a topological uncertainty, which is, are loads connected to which phases? What is the line parameters? There could be consumer load uncertainty, how much DER is connected, and what load profile should we be selecting. Then there could be electrical market-related uncertainties, price volatility or policies uncertainty that we'll be talking about later. And there could be extreme events. And essentially, we can model them as a random variable or a continuous variable, which we'll, of course, not be discussing in this presentation. What we'll be talking about is 3 use cases, and there is something that we can learn from this. The first use case that I would like to highlight is selection of representative networks, especially for the context of Europe. So my previous distinguished speakers talk about the need for more data. I think I would like to counter that we need better data and good data rather than a lot more data. And in this case, what we did is we tried to select representative networks. And why do we need representative networks? Europe has 18 million kilometers of lines. We have more than 300 million electricity customers served. There is a large amount of energy served. And we have more than, this is a tentative and approximate number, we have around 4 to 5 million low voltage substations. So we need, we have numbers for UK where it's definitely more than 1 million. And what we need to do is select a small subset of these samples to make better decisions and test our algorithms to it. So in order to do that, this selection of representative feeders provides us scalability, benchmarking, and in order to cater to the scarcity of the publicly available data set. And the objective of these application could be, if we are doing congestion management or historical measurement application, we can create sensible ballpark estimates. We can provide policy recommendations, testing time of use tariffs, for example, and also for planning. So with these applications in mind, we propose a selection of representative feeder where we try to extract certain attributes which are related to the graph or the topological graph of the feeder, the electrical characteristics, geographical and load-based characteristics, and we try to select a smaller subset of feeders which we call representative sets of feeders. So with the skeleton of algorithm provided here, we applied it to 4 data sets. The first data set was from ENWL in the UK, where we reduced the number of representative feeders from 128 feeders to 4 feeders. And similarly for Spain and Netherlands, and then also provide reconfigurable test cases which was otherwise missing previously. So this is available online. The second use case that I want to talk about is consumer and DER load profile. I have often heard that we don't have enough load profile for which represents low voltage consumers. And I would disagree with it, because there is a lot of data, oftentimes not very streamlined and easy to access, but it does exist somewhere, and it requires a lot of effort from someone to possibly to clean the data, fill the missing data, and make it usable. So what we did here is we looked into 3 data sets. The first from the Netherlands, which was about electric vehicle charging. The second was the PV data set from Elia. And the third data set was the 2022 load profiles from Fluvius. So we aggregated these load profiles and made it usable for possibly simulations that you might do at your own end. The first data set is the EV charging profiles, which contains more than 10,000 charging events in the Netherlands. And we tried to extract these 5 attributes, which is the arrival time, departure time, the charge time, the peak time, and the charge energy. And with these, we can create like a synthetic scenario generator for EV charging profiles, or possibly use this data set right away. And this can be used, can be integrated within applications such as decision makings within the distribution network. The second data set is the PV. So we try to create a CDF of the distribution, and we can create scenarios for PV generation considering the historical aspect and the weather situation. And the third is about the consumer types. So we'll Fluvius categorize these load profiles into 5 consumer types, and we try to create a repository for these consumer types, which can be used in a faster way, whether they have EV, PV, or heat pump, or all of them. And this repository can be accessed here with the QR code. The final use case that I'll be talking about is once we have the load profile scenarios, and these load profiles are repeating in itself, can we create representative scenarios or a smaller subset of scenarios which does represent the whole data set? I'll not be talking about the third use case in detail because I'll be presenting this in, I think, tomorrow. In this paper, what we do is we propose the scenario reduction technique using the statistical attributes of the load itself. So this framework is dependent on the CDF and its distribution, and we create buckets in order to not discount the extreme load scenarios. With these smaller subset of scenarios, we want to test whether the decisions that we make are optimal or not, which is not part of this work, of course. So this is the presentation that I'll be doing tomorrow. So for more details on this reduction in scenarios and how does it make sense, so we'll be providing 3 use cases to validate that reduction of scenarios indeed makes sense. Now, scaling stochastic problems is a big challenge, as I showed. So the first approach that we used is a reduction of the number of feeders or the networks to be considered. And the second is, can we use representative days or representative instance of simulation in order to make decisions which can help different entities in power network, which can be an aggregator or a system operator. The last use case that I want to present is how policies are also very fragile. In California, in 1995, they had a net metering contract in which consumers were allowed to connect to the grid, and they were provided equal amount of injection and consumption tariffs. But as the amount of DERs increased in California, after 22 years, they revised this policy to net metering 2.0, where now the injection is not as beneficial for consumers to install DER at their end. And recently, after 6 years, or in 2023, they again modified the policy to net metering 3.0. Now, this is even less incentivized for consumers to connect or install DERs, but it is more beneficial for consumers to install a storage device. With this story, I would like to conclude my presentation. So I provided that decision support tools need to cope with parameter uncertainty. And this uncertainty, if modeled properly, needs some sort of a scaled-down version or a reduction, which we call as representative cases. We also talked about representative feeders, and why is it important? Because there are millions of feeders. And we have to have a physical understanding of the load and consumption model in order to make this integration without ignoring the physics of such variation. Thank you.
Is this working? Okay, great. Thanks everyone for the great talk. We are out of time, unfortunately. But what we can use the remaining time, like maybe the next 5 to 10 minutes, is to take some audience questions for the panelists. And then if there are still other thoughts or questions, then you can continue in the tea break. Yeah. Is there a mic or something that we can use? Okay, thank you.
Yes, so thank you. My name is Gern Oogensteen from the University of Twente. So indeed, I also already for a long time advocate for more data. I have a question for the last speaker because indeed I agree with you that you need to have less but very good data and maybe even more towards the corner cases. But you also showed load profiles, and to me these are really static. Then you talk about markets. But these markets will, of course, influence user behavior. So to what extent do you believe that static load profiles are suitable for future developments of load profiles?
Yeah, thank you for your question. It depends on the application. So, of course, it needs to be trimmed based on what we are trying to do. And we have looked into one problem specifically a lot, which is hosting capacity of networks. And when we do hosting capacity, even for a small feeder, considering all the uncertainties possible, it will take hours and hours of simulation. Now, if we have to scale this to, if not millions, but thousands of networks, this is not the correct way to do it. We have to inject uncertainty possibly in some other different way or select some of these subsets. So what we argue, and I'll be talking about it tomorrow, is can we use weighted scenarios rather than all scenarios of equal weight, and just increase the number of Monte Carlo simulations, which will essentially explode the problem. So these smaller subsets which are weighted are as good as, if not, to solve the problem, and we show that these error bounds in decision making is within, say, less than 5%. Now, this bound can be, of course, reduced as we increase the computation availability, but the argument is, considering there are millions of them, the computational scalability would not be catching up as fast as what we have to make in the real world. Thank you.
Thank you.
Right. Anyone else in the panelists who would like to respond to that? Perhaps Jaco from the DSO group?
No. Yeah, I think it's a quite good question. We also sometimes use try to find representative grids so that you don't have to calculate all the grids. And I think for some studies it's very useful. But for instance, yeah, in the end you want to integrate a certain customer at a certain grid, then you have to focus on that specific grid with that specific load. So, but I think there are quite some use cases where representative situations are very useful.
All right. Any other questions? We still have a couple more minutes. Okay. Thanks.
Thank you.
So hi, this is Claudia from the Technical University of Vienna. I also have a question to Jakob. Regarding the synthetic data, you showed a graph saying power. So is this active power or reactive power? Because we've made the experience that when trying to create a synthetic data set, these two behave quite differently.
Yeah, good question. This example was on active power, because on reactive power we don't have that many measurements, especially for customers at the radar scars. We also did some research on that, but we are not there yet to publish synthetic data sets out of there because the training data is quite limited. So we will know much more about active power than reactive power. That's absolutely correct.
On that topic, like, can you also say a bit about what happens with extreme cases? Because we have, of course, like all the problems with climate change and weather patterns are shifting over time. So if you're using historically collected data to generate synthetic data, that's not necessarily forward-looking. And it might lead to problems with underestimation of certain risks, let's say, or like mischaracterization of uncertainties in the problem. Is there a way that you are considering how to address that? Open question to all the panelists, but you can start, Jaco.
Yeah, I think definitely that there are some changes that are not in our historical data, so we have to retrain, for instance, the synthetic models in 1, 2, 3 years from now again, and make new data sets. We're not satisfied in publishing one data set and now it's done. Batteries are now not present in our data sets, and hopefully there will be more in the coming years. There are more examples, which is not in the historic data. Yeah.
All right. Good. Yeah. Hisham?
Yeah, we're working on training gray box models for the different archetypes of buildings, and obviously the outdoor weather condition will be some of the inputs. And at the same time, we have to work on having future climate scenarios and extreme scenarios for the local region, especially if you take countries where topology is quite varied, like Norway, and so that then you can test what will happen in that building or that type of buildings, therefore the energy demand for 2050 or 2000. So probably gray box models calibrated with the real data that we have, together with working a lot on extreme scenarios for the future. Yeah.
Yep. All right. Fantastic.
I think the black swan events are going to be, of course, a problem when we consider data-driven models. And how do we consider it? It depends on the application. So for the applications in decision support that we are doing, it's not as critical because the failure leads to only the regional, it affects only a small region. But I think in transmission network, these needs to be considered with more thoroughness and fail-safe, so that the system under those extreme black swan events also are operating, and maybe that's why the grids are designed with multiple parallel paths. But for distribution network, I think we are not yet looking at it as much as traditionally transmission networks have been working on it.
Yep. Okay, fantastic. Chris, maybe you also would like to add something about these black swan events with your controllers, because you were also talking about injecting physics into the RL agents and stuff like that, and perhaps that's also a way of mitigating some of the uncertainties.
Yeah, that's one way indeed. But yeah, from the residential perspective, a big uncertainty is also user behavior and how to deal with that. So, and that's why we typically try, mostly in the European projects we're participating, user studies are still there. And I think specifically for residential and building environment, this is still a very valid field of research, complementary to the technical things we are doing. And that's sometimes, at least in scientific publications, this gets overlooked. But in practice, that's a kind of an important thing. Also, yeah, user awareness and creating the awareness and the willingness to participate, because that's even today with the renewed or increased awareness of energy and climate change. Even nowadays, it's still, in some cases, hard to convince people to participate in trials, for instance. So I think that's another factor of uncertainty that we need to deal with.
Indeed. Yeah. All right. Fantastic. And I guess like the last question that I have, and maybe we can come to the crowd after that, is perhaps like this kind of modeling of interactions, because if you're looking at synthetic data, that's typically done in a, let's say, static kind of way. Also going back to the first question, that this is like, let's say, a snapshot of the past, and then we are trying to learn something about it. But perhaps the most complicated interactions are between buildings and users, for example, or between energy consumers and the energy markets. And these are typically, let's say, two-way flows of information, but that's completely missed in many of these types of models. I was wondering, perhaps, Martha, if you would like to share some thoughts or opinions on how we can include this, let's say, two-way communication in these kind of things.
I don't really have a good answer to that. It does, though, raise an interesting point that the network operator owns the network data, and it is unlikely or not obvious that they would share it with an aggregator or building management system operator, and then except, well, perhaps through markets to some extent, but that is, of course, this compartmentalization of data is also one of the bottlenecks to a more efficient, a grid-friendly operation of distribution energy resources and loads.
Yep.
So, not an answer to your question, but I think something that is sometimes overlooked, perhaps.
Yeah. I agree with that. I would say like this compartmentalization is necessary because we don't really have too many initiatives at the moment. So it's like people working in their own silos. And hopefully by the time we have next ISGT, maybe there will be a bit better and more conversations. But yeah, we had a question there.
Hi, my name is Katharina. I'm from ETH Zurich. And I totally agree that we need more measurement-based data. For the synthetic data, I'm wondering, or I'm trying to understand the trend to go more to learning-based approaches versus using simulation-based load profiles, for example, for customer data, or like customer residential load profiles.
For me, yeah. So what I was talking about was more learning-based load profiles. So learning, yeah, we can access and analyze smart meter data for a lot of customers, and we can train an AI model to learn all the different patterns out of it. Because with simulation-based, it will cost too much time, and then after 1 year you need to do everything over again because there's a new appliance or the weather is different, and so then learning-based algorithms are more time-proof because you just can retrain the same model again and have an updated data set.
Yeah, on the building side, simulation data, much easier to generate, can be very nice for pre-training models, and then you fine-tune it with just the data of your target building. So that has been tested, transfer learning with that works a lot. So there is a lot of use for simulation data. Yes.
Okay, thank you.
Great. Any last questions? Because we are already almost 15 minutes over time, so there is one last question, then we can take it. Otherwise, we go for a tea break. Okay, well, let's thank our panelists. Thank you. And see everyone back at 4:30.
Kull darba li tkun hawn, kbira kontra l-ħin. Jitwaħdu n-nifsiet, suritna melusi. Fuq spalti nħossu ftik nishtiqin. Xewk